Hello, my name is Anna Bondarenko, and I would like to thank the organizers for giving me the opportunity to present the work that I've done during my PhD at the University of Groningen under supervision of Jasper Knoester and Thomas Janssen. The title of my talk is Multiscale Modeling of Structural and Optical Properties of Supramolecular Tubular Aggregates. I will start by introducing tubular molecular aggregates, present a multiscale approach to model structural and optical properties on the example of CT3 aggregate, and I will talk about the results and discussion, followed by summary and conclusions. Supramolecular aggregates may assemble from a variety of building blocks, resulting in interesting properties. For example, green sulfuril bacteria uses tubular supramolecular aggregates called chlorosomes as light harvesting antenna in its photosynthetic system. Chlorosomes are composed of closely packed bacterial chlorophyll molecules, and the role of chlorosome is to collect photons, transform them into the excitation energy, and transport the energy to the reaction center where electrons can be extracted. There is something remarkable about the green sulfuril bacteria, which is the evolution has designed a highly efficient light harvesting antenna for these bacteria. And this allows bacteria to live in extremely low light conditions, sometimes getting only a few photons per hour. The quest to recreate such efficiency under laboratory conditions has sparked numerous studies of synthetic self-assembled systems which mimic natural chlorosomes, for example using porphyrins, zinc chlorine, and cyanine dyes. Supramolecular aggregates of synthetic dye molecules are easy to assemble and offer great perspectives to prepare biomimetic functional materials for light harvesting and energy transport. We studied these double-wall cyanine aggregates, and their double-wall structure is close to the multi-layer nature of the chlorosomes. These interesting functionalities are governed by the excitonic properties. The individual molecules within the aggregates of the double-wall CT3 aggregates are closely packed and held together via non-covalent interactions. The close packing interactions give rise to the aggregate's collective properties. The collective states or excitons are delocalized or shared by many molecules of the aggregate. And the result of such delocalization, the absorption spectrum of the aggregate is redshifted, narrow, and has more structure in it compared to the broad monomer spectrum. It is important to note that the excitonic properties and thus the optical properties of the aggregates are highly sensitive to the aggregate structure and molecular packing in it. The important question is, what is the relationship between the structure and optical properties? In order to understand the functionality of existing system, or furthermore to design new materials, we need to address this question. Experimental resolution is not enough to see the details of the structure. Cryo-TEM images give information about the radius and length, however the molecular packing is not resolved. Ab initio modeling of such a large and complex system is just not feasible. So the common approach so far was to use phenomenological modeling, which gives a good starting point and very useful information. However, it is still doesn't give a realistic picture. So we need a modeling approach that combines a proper and detailed description of the structure and optics. For this, we use molecular dynamics to address structure, and we model absorption spectra with Frenkel Hamiltonian. And finally, we rely on comparison to experiment to validate the model structure. I would like to stress that we cannot do with a method which takes into account only structure, nor with a method which only cares about optical properties. We really need to combine the two methods. Here is the workflow of the multiscale approach that we're using. First, we construct perfectly ordered starting structures, exploring the structural parameters within the available experimental constraints. Then we pre-assess the optical properties of such perfectly ordered structures. By this pre-assessment, we discard structures which lead to evidently off-target optical properties. Then we perform MD simulations on the pre-selected structures to assess their stability. And then for stable tubes, we can assess structural disorder, meaning deviations from perfectly ordered packing. For stable aggregates, we perform microelectrostatic calculations that include the effect of electronic polarizability. With this, we obtain the influence of the local environment on the molecular excitation energies. And finally, we calculate absorption spectrum based on the obtained MD structure, where we include both types of disorder. This leads to broadening and shifts of the absorption peaks compared to the spectrum obtained in step 2. If the resulting spectrum does not agree with the experimental reference spectrum, we use the collected insights as feedback and iterate over again. When the resultant spectrum agrees well with the experimental spectrum, then we have the validated molecular model. To construct structures of the CTS3 double wall aggregates and validate our modeling, we use experimental spectrum as the reference. This complicated spectrum shows two sharp, low energy peaks and several broader, higher energy peaks. The lowest energy peak is associated with the inner wall and the upper one with the outer wall. The two peaks are separated by 300 wave numbers and are both polarized parallel to the tube's axis. The two walls are coupled structurally but do not share excitonic states, so we treat them as uncoupled. Higher energy region associated with the contributions from both walls is polarized perpendicular to the tube's axis. Moreover, based on the previous phenomenological modeling, we know that a rich structure in the experimental absorption spectrum suggests that the underlying lattice has 2 molecules per unit cell. So we start from the crystallographic unit cell of a similar molecule. We construct a herringbone lattice, which we roll onto cylinder along the rolling vector. The length of the rolling vector is equal to the circumference of the obtained tube. We use experimental values for the radii to define the length of the rolling vector. The rolling angle is not known, so we keep it free. We construct inner wall and outer wall separately, and each molecule is associated with its transition dipole moment that we will use to translate structure into Hamiltonian. When we process structures, we make sure that the calculated spectrum agrees with the conditions obtained from the experiment about the order and polarization of the peaks. Next, the constructed double wall structures is dissolved in water with counter ions. The obtained system is pretty large, containing up to 7,000 di molecules or 4.2 million of atoms. We can map transition dipole moments on the molecules from the MD structures. Structural disorder obtained from MD then translates into the disorder in the intermolecular resonance interactions, or of diagonal disorder, which depends on the angle and distance between transition dipole moments. We use microelectrostatic calculations to compute energy shifts in the molecular excitation energies due to environment. We calculate the interaction between the central molecule and its surrounding, take into account polarizability and electrostatic effects. All MD simulations and microelectrostatic calculations were performed by our collaborators in the MD group of the University of Groningen. To calculate absorption spectra, we use Frenkel exciton Hamiltonian, where the first term is the excitation energies of the molecules, their diagonal elements. And the second term is the excitation transfer interactions, there of diagonal elements. We include diagonal disorder from the Gaussian distribution of the energy shifts obtained from the microelectrostatic calculations. And of diagonal disorder, we include directly by mapping transition dipole moments from each MD snapshot. The absorption spectrum is then given by this formula with the oscillator strands and corresponding energy of the exciton eigenstate. Double brackets mean the average over the snapshots from MD trajectory. Finally, we've got an optimal structure, and here's the calculated spectrum in red, shown compared to experimental reference in black. The agreement is not only in the overall shape, but also in the essential details, such as the contribution from the inner wall and outer wall are correct, the relative oscillator strength is reproduced correctly, as well as polarization of the peaks. And high energy region shows polarization perpendicular to tube's axis. The model spectrum reproduces correctly the line widths, the only contribution that we added is the homogeneous line width. In principle, time correlation functions could be extracted from the MD trajectories, but this was beyond what we were trying to achieve here. Now that we have a validated model, we can answer the question about the origin of the energy splitting between the inner wall and outer wall. Assuming that the underlying lattice is the same for the inner wall and outer wall, it is not possible to explain the energy splitting between the lowest energy optical peaks of the both walls, polarized parallel to the tube's axis. And this is because the energy position of the parallel component of the spectrum of a cylindrical aggregate is essentially independent of both Rayleigh vector and the tube's radius. Another hypothesis that we had was related to a different energy shift as a result of the curvature, meaning that molecules in the inner wall and outer wall experience different environments and thus have a different energy shift, which can explain the energy splitting. First, we calculate the energy shift including only surrounding dye molecules, and indeed we see that the average energy shift in the inner wall is different to the one in the outer wall. However, when we include in the calculations the solvent molecules, we see that the effect is the opposite and is fully compensated. And the compensation effect comes from the counter ions. So this leaves us with the explanation that the energy shift is due to the slight difference in the packing density in the both walls. A high density in the inner wall compared to the outer wall would ensure stronger excitonic couplings and, as a result, larger redshift. It turned out that constructing starting aggregate structures by increasing the in-plane unit cell lattice constants for the outer wall by mere 2.5% compared to the inner wall is enough to match the energy splitting in the experimental spectrum. NMD simulations confirm that such tubes are stable. Our model provides a detailed quantitative picture both on static and dynamic disorder. In a follow-up work, this model combined with the experimental ultrafast experiments allowed us to resolve the origin of molecular and excitonic disorder in CSS3 nanotubes. We showed that although there exists considerable disorder at molecular scale, the disorder is significantly suppressed at the excitonic level due to the exchange narrowing. You can find more information in our recently published paper. To conclude, we successfully combined MD simulations, microscopic calculations, and optical modeling to study CSS3 tubular molecular aggregates. The proposed multiscale approach is a powerful tool to understand structure-optical property relationships. The model opens the way for detailed exciton dynamics studies and these chlorosome mimicking systems. And finally, I would like to thank all the people involved in this work, my supervisors, our colleagues from the MD group, and our experimental colleagues, all from the University of Groningen. And currently I'm working as a postdoc at the Northwestern University in the group of Roel Tempelaar. And thank you for your attention.